Analysis 2, it is module 5, an introduction to stiffness method, which is based on the displacement method. Now, this is extension of the displacement method. We are done with the force method. Now, topics to be covered, it will include methods of analysis for indeterminate structures, kinematically indeterminate. Remember, now we are not dealing with the statical indeterminacy. We will be dealing with the kinematic indeterminacy. Kinematic means freedom to move. Now, matrix analysis and methods, introduction to stiffness method of analysis, stiffness of a member, kinematic indeterminacy, general procedure of stiffness method, stepwise procedure of stiffness method, then example 1 and 2, comparison of stiffness and flexibility method. We will discuss computation of member end actions, and then fixed end actions. Now, following are the methods used for the analysis of indeterminate structure as discussed earlier. So methods, we were having classical methods, which you discussed in the 4th semester. And then matrix methods, in which we discussed we finished the flexibility method, stiffness method, now we are discussing. In classical methods, you discussed the consistent deformation method, slope deflection equations, and then moment distribution moment and 3-moment equation. Now, globally, there are 2 ways to analyze indeterminate structure. One is force-based methods. Other is deformation or displacement-based analysis. Force-based analysis, it involves the calculation of reactions of the supports and determination of internal actions, normal force, shear force, and bending moment within the structure. Deformation-based method, deformation analysis involves the evaluation of deformation, displacement, and strength of the elements of a structure as well as whole of the structure. Now, matrix analysis of structure is a branch of structure analysis in which matrix algebra is used as a tool for analysis of structure. Objective of analysis of a structure is to predict the behavior of a structure due to external loads, temperature changes, settlements of supports, and vibrations, etc. Now, matrix methods, flexibility, force method, and then we have stiffness or displacement method. We discussed the flexibility method, and let me review that again. In this method, redundant constraints are removed and corresponding redundant actions, force and moments are placed. An equation of compatibility of deformation is written in terms of these redundants and corresponding displacements. The redundants are determined from these simultaneous equations. Equations of statics are then used for calculation of desired internal action. In this method, actions are treated as basic unknowns. Now, coming to the stiffness or displacement method, what do we have here? In this displacement method of analysis, the equilibrium equations are written by expressing the unknown joint displacements in terms of loads by using load displacement relations. The unknown joint displacements, that is the degree of freedom of the structure, are calculated by solving equilibrium equations. There we were using the compatibility condition. Here we will be using the equilibrium equation. Now, very slowly I'll explain now, and you just try to get it. In compatibility, what we did, we removed the redundant action, and once we removed the redundant action, we got the displacement there, which was not there initially. So that displacement, it was causing now the compatibility issue. And to resolve that issue, we applied the unit effect multiplied by the AR, and we brought it back to the compatibility condition, the initial compatibility condition the indeterminate structure was having. You must be clear about this concept now and this technique which we were using in case of the statical indeterminate structure in case of the flexibility method. Now, in case of the stiffness method, what we do, we have a hinge support. So what is the degree of freedom of hinge support? It can allow the rotation. It cannot allow the horizontal translation. Why? Because it can offer the horizontal resistance. It does not allow the vertical translation. Why? Because it can allow the vertical reaction. It can allow the rotation. Why? Because it cannot resist the moment. Moment component is not going to be there at the hinge support. So means it can allow the rotation. अब rotation को आप कैसे prevent करेंगे? When you clamp this, how we clamp it? We provide just a fixed support there. Okay, you have made this kinematically determined by restricting, by stopping the rotation. Theta तो आपका zero हो गया, but what happens when you clamp this and when you are not allowing the rotation, what will happen? The moment will be generated there now, which is not there in the original structure. Now, when moment is generated, so it means you are violating now the equilibrium condition. Moment was not there, but now you are providing moment there. It is generating moment there. So what we do? अब इस मोमेंट को आप क्या करेंगे? You need to bring them in the equilibrium condition. वही zero पे आप लाएंगे, and we apply now rotation in such a way that it gives you the original zero moment. Rotation and moments are generated. We write an equilibrium equation, and by doing that, we can find out the unknown joint displacement, which is rotation in this case. So यहाँ पे कौन सा equation आपका involve हो गया? Your equilibrium equations instead of the compatibility equations. Now equilibrium equations are involved. Displacement method of analysis is preferred to computer implementation. So remember, is everybody will be having the same kind of the kinematically determined structure. So it is very organized and very simple also as compared to the flexibility. You don't have much choices now here. Stiffness, what is the definition of the stiffness? Stiffness of a member measures its resistance to deformation, how stiff it is. So it measures the resistance to deformation. And what is its definition? The stiffness of a member is defined as the force which is required to be applied at some point to produce a unit displacement now. Force required to produce unit deformation when all other displacements are restrained to be zero. So this is the force required to produce unit deformation. Or what we do, we provide a unit deformation now. Flexibility में हम क्या करते थे? In flexibility, we were providing the unit action. Now here we will be providing now unit displacement and we'll be finding out the forces now produced. If a member which behaves elastically is subjected to varying axial tensile load, W as shown in the following figure now, and a graph is drawn of load W versus delta, the result will be a straight line as shown in figure 5.2. The slope of this line is called stiffness. So here you can see. When load is W, displacement produces delta. When load is 2W, the displacement linearly proportional. Now the slope of this line, it is known as the stiffness. Here you can show it to the axial load. This W is applied and this is the delta produced, and delta is directly proportional to the W. So here you can see mathematical S is equal to, this is the stiffness now, W divided by A. S is what? It is now the slope of this line. So what will be the slope now? it will be W divided by this delta, this slope theta. It is known actually as stiffness, which is S. So here W divided by delta. In other words, stiffness is the force required at a certain point to cause a unit displacement at that point. Equation 5.1 can be rewritten, so just rearrangement of this equation, W is equal to S times D, where W force at a particular point, S is the stiffness. Sometimes it is denoted by K also. So K or S we will use as a symbol for the stiffness, and delta is the unit displacement of the particular point. Now the above equations relate the force and displacement at a single point. This can be extended for the development of a relationship between load and displacement for more than one point on a structure. Here now, that concept again, we discussed this for the flexibility method. Action is applied, action is increasing, displacement is increasing. And we say this displacement is directly proportional to A. Remove the proportionality sign, D is equal to FA, or F is equal to D divided by A, where F is the flexibility of the spring. Displacement produced by a unit action. Our A is directly proportional to D now, so A is equal to ST, or S is equal to A divided by D, where S is the stiffness of the spring. Again, now we showed that this flexibility is reciprocal to the stiffness. Our stiffness is reciprocal of this F. So this is how it was shown. Now kinematic indeterminacy we are coming. So this will be now your task to understand the kinematic indeterminacy. Degree of kinematical indeterminacy is the number of unconstrained degree of freedom to move now, or displacements. You will be looking at the joint or at a point, and you will see how much capability it has to move or to allow the displacement. If it is not allowing, so it means it is kinematically determinate. Otherwise, depending on the number of now these displacements, you will be counting those one, and that will become the degree of kinematic indeterminacy of that particular joint. For the whole structure, you sum those unknown displacements, and that is becoming the total kinematic indeterminacy of the structure. In kinematic indeterminacy, we measure the total number of degree of freedom possible at a joint, at joints. A structure is said to be kinematically indeterminate if the displacement component of its joints cannot be determined by compatibility conditions alone. That is, number of unknown joint displacements over and above the compatibility conditions will give the degree of kinematic indeterminacy. Now, with examples, we will explain this. Kinematic indeterminacy for two dimension. Now, fixed support gives three reactions. Three reactions when we have, it means it is not allowing any displacement now. What are these three reactions? One, moment, and two, forces. Now, when it is not allowing, when it is having moment, so it means it is not allowing rotation. And when it has two forces, means horizontal and vertical, so it means it is not allowing horizontal and vertical translations. Means we don't have any translations, we don't have any now rotation, so it means the degree of freedom of a fixed support is zero. It is not allowing any kind of displacement, so it is kinematically determinate. Degree of freedom or degree of kinematic indeterminacy is zero. Hinge, when we talk about a hinge, so it allows two reactions, means horizontal forces, both horizontal force and vertical forces, but no moment reaction. It is not allowing any now moment reaction. So kya hoga when we don't have moment reaction? It means it is allowing rotation. Hence, degree of freedom at a hinge is 1, and that is the rotation. It is allowing only rotation. Now, roller gives one reaction in translation direction, hence degree of freedom at roller is 2. अब क्या होगा? Let's roller, it is resting on a vertical surface now, so it means it is offering resistance in the vertical direction. Means it is restraining the displacement in the vertical direction. Horizontally it can move and it can rotate also. So it is having 2 degrees of freedom now, one rotation and one translation, which is written here. For a two-dimensional rigid joint or free and the number of degree of freedom at a joint is 3, and it will be one rotation and 2 translation, vertical and horizontal translation. And for internal hinge, the degree of freedom is 4 now. Why 4? Because it will be allowing independent translations to the left side and to the right side members. And it will be allowing a horizontal translation and a vertical translation. So we have 2 translations and 2 rotations now in case of the internal hinge. So it is giving us a 4 degree of freedom situation. 3 degree of kinematic indeterminacy for 3 dimensions. Now fixed support gives 6 reactions, means 3 moments and 3 reactions, 3 forces now, means it is a kinematically determinate structure. It is not allowing any kind of rotation and it is not allowing any kind of translation. Hinge gives 3 reactions all in translations and no rotation reaction, hence degree of freedom at hinge support we are saying now. It will be allowing 3 rotations, so it means it is 3 degrees kinematically indeterminate. The degree of freedom is 3. And translations it is not allowing in any direction, so it means in terms of the translations it is determinate, but in terms of the rotations it is kinematically indeterminate. Roller gives 1 reaction now, so 1 reaction. So it means it is allowing 2 translations and it is allowing 3 rotations now. So it is 5 degrees kinematically indeterminate. For a 3-dimension rigid joint or free end, the number of degree of freedom at a joint is 6 now, and it will be 3 rotations and 3 translations. For internal hinge, the degree of freedom is 9 degree, means 6 independent rotations and 3 translations. Now, a simple equation, how we find out this kinematic indeterminacy. So, kinematic indeterminacy will be equal to 3j minus r plus I. J is the number of joints, r number of reactions, and I is the number of internal hinges. Now, ignoring axial deformation, sometimes it will be given that you ignore the axial effects. If we ignore the axial effects of deformation, then the kinematic indeterminacy will decrease, which we are ignoring. Why we are ignoring axials? Any idea? So you should be clear, because the axial rigidity will be more and the axial effects will be less. So that is how we can ignore the axial deformation in case of the rigid joints, frames especially. Kinematic indeterminacy after ignoring the axial effects, it will be kinematic into 3j minus r plus I as we did, and minus the number of members now, where we are ignoring the axial effects. This is now kinematic indeterminacy, how we find out. The top one you see a cantilever beam, left support is fixed, the right one is now free. It is a 2-dimensional problem. So 0, when you see with the fixed support, it is for its degree of freedom. Zero means it is not allowing horizontal vertical translation and it is not allowing the rotation. But the right support, which is freed of free joint, it is allowing, it can settle down, it can move to the left, right, and it can rotate also. This 3 is showing it is 3 degrees of freedom. So kinematic indeterminacy for this whole beam now, 0 plus 3 is equal to 3 degrees. Now, if we apply that equation, so J is 2, R restraints, here we have 3 restrictions. These 3 now reactions at support, fixed support now, which is the left support, vertical, horizontal, and then the moment now. So kinematic indeterminacy is 3 times 2 minus this J, which is 3. So we are getting the same 3 now. Ignoring axial deformation in one member we are ignoring, so minus 1 now, so 2 degrees if we ignore the axial effect. So it is becoming 2 degrees kinematically indeterminate problem. Second now sketch, left we have hinge support, right we have a roller support. This one is showing it is allowing only rotation now, hinge support. This too, it is allowing horizontal translation as well as a rotation here. So kinematic indeterminacy, it is 1 plus 2 now is equal to 3 degree, 1 from here and 2 from here. R, J is equal to 2 joints we have. R, we have 3 reactions now, vertical and horizontal at 1 and vertical at 2 now. These are 3's. Now kinematic indeterminacy is 3 times 2 minus, so 3 degrees. So you see here, the same we have. If we ignore the axial effect, so one member we need to subtract now, so it is becoming 2 degrees kinematically indeterminate. Coming to the third sketch now, left hinge support, so we have 1 degree of indeterminacy, that is rotation. At 2, the middle support, it's a roller support, so we have 2 degrees of indeterminacy, horizontal translation and rotation. And then the right support, again a roller support, so we have horizontal translation and a rotation, so 2 is written here. This is 1 plus 2 plus 2, 5 degrees indeterminate. If we apply this equation, so again we are getting 5 degrees indeterminate. If we ignore the axial effect, so we have 2 members now, so minus 2, so this is becoming 3 degrees now. Coming to the last sketch, at left we have hinge support, so 1 degree of freedom. In the middle we have this this circle, so we have 4 degrees. And which one are those 4 degrees? 2 translations and 2 rotations now. And at 2 we have 2 degrees, which is 1 rotation and 1 translation. If we add them up, it is becoming 7 degrees kinematically indeterminate. It is written here. And you can go with the number of giants and these restraints. So again, 7 degrees. If we ignore the axial effects, so 2 members, axial effects we are ignoring. So we subtract those and it is becoming 5 degrees indeterminate. In case of the frame now, we have in this left top one, we have 4 giants. What is the situation at the bottom giants? We have fixed support. So these are now kinematically determinate, this bottom one. But the top one, each one is having 3 degrees of indeterminacy. So 3 plus 3, it is becoming 6 degrees indeterminate. If we want to use this equation, so number of giants, it is 4. Number of reactions, 3 at this left and 3 at the right. So 6. Now we 3 times the number of giants minus this 3 is coming. Each giant is offering how many degree of freedom? 3 degree of freedom. 3 times the number of giants. This 3 is coming from the 3. If there is no support, no restrictions, so it will be offering 3 degrees of freedom now. Now we are taking away now this 6. Why? Because left and right bottom, these can offer 3 reactions. So 6 is 6 degree. If we ignore the axial effect, so 3 members, so minus 3. So this is becoming then, in that case, if we ignore the axial effects, it is becoming 3 degrees indeterminate. Coming to this one, now number of giants. How many giants we have? 1, 2, 3, 4, 5, and 6. So J is 6 reactions now. 2 here and 1 here, 3. Internal hinge condition is 1. So 3 times 6 minus 3 plus 1, this is 16 degrees indeterminate now. If you start counting this, now 1 degree here at this support, 3 here, 4, 4 at this internal hinge. We have how many? Now 4 plus 4, 8, then 3 here, 11, 3 here, 14, and 2 here, 15 and 16. So just by observation without using this equation, it is coming this 16 degrees. Now if we ignore the axial effect, so 1, 2, 3, 4, 5 members, so it is becoming 8 degrees. Similarly, you can find out for this situation also. 10 degrees, how 10 degrees? 2 here at this support, then 3 and 3. So 6 and 1 here at this hinge support, we have 1 only rotation. So 7, 8, 9 and 10, 2 are coming from here, 10 degrees. So if we ignore the axial effect, so it is coming 4 degrees. Now, I think, shall we now start this procedure also, or you want to go and you want to be familiar with how we find out the kinematic indeterminacy? Any question about the kinematic indeterminacy? Okay, if no questions, so should I start now the general procedure of stiffness method?
सर इट्स इनफ.
It's enough. ना लेकिन अगर इसको हम स्टार्ट,
सर ये तो नेक्स्ट क्लास में कर लेंगे.
वो तो ठीक है, मैं कहता हूँ ना कि अगर हम सिर्फ ये प्रोसीजर इसको कर लें, दिस वन, और आप इसको थोड़ा सा रिवाइज कर ले, और नेक्स्ट टाइम जब आप आ जाए तो हम ये प्रॉब्लम्स वगैरह पे चले जाए. अगर आप कहते हैं कि नहीं, वी नीड टू स्टार्ट नेक्स्ट वीक, तो नेक्स्ट वीक से फिर कर लेंगे.
यस सर,
क्वेश्चन के साथ करेंगे, ज्यादा समझ आएगी.
नहीं, मैं तो यही कह रहा था ना
Next
कि अभी
week
अगर
करेंगे.
प्रोसीजर में एक्सप्लेन कर लूं तो फिर आप क्वेश्चन पे आप समझेंगे ना, लेकिन आप कहते हैं कि नहीं, आने वाले में आप ये भी एक्सप्लेन कर ले और प्रॉब्लम भी कर ले, तो इस तरह भी कर सकते हैं. टुडे वी आर इन द 5th लेक्चर, राइट?
यस सर.
अच्छा, इस तरह करें आप, ये काइनेमेटिक इंडिटरमिनेसी, डिग्री ऑफ फ्रीडम, ये चीजें जो है ना आप समझ लें इस सारी चीजों को. फिर जब मैं कहूंगा ना कि आई एम मेकिंग दिस स्ट्रक्चर, इसको हम रिस्ट्रेंट स्ट्रक्चर कहते हैं. सो यू शुड नॉट बी आस्किंग मी क्वेश्चन के D1 आपने किस तरह लिया और D2 आपने किस तरह लिया. या अगर मैं कहता हूं कि दिस स्ट्रक्चर इज काइनेमेटिकली इंडिटरमिनेट टू 3 डिग्री, सो यू शुड बी वेरी मच क्लियर अबाउट दिस, कि दिस इज 3 डिग्री एंड फ्रॉम वेयर दीज 3 डिग्रीज आर कमिंग. Okay, you can ask me if you have any question, otherwise I'll leave and we are done for today. Okay, if you don't have anything to ask, so here we are going to stop now. Okay, so we will meet inshallah coming week the same time. Thank you so much.